Hi friends, let's have a look at problem 3473, sum of key subarrays with length at least m. In this video, we're going to give a solution based on dynamic programming. So this problem is marked as medium. Actually, it takes me some time to figure out clearly what's going on. So actually here the problem statement is very short. So we are given an integer array called nums and two integers k and m. So we want to find the maximum sum of key non-overlapping subarrays of nums, where each subarray has a length of at least m. So here we have two examples. I'm going to post analyzing the two examples. After we finish the coding, I'm going to print out some information and then digest the two examples. That will be easy. Actually, as a human being, if you just screen this explanation, it's rather straightforward to digest and understand the output. So here the constraints are the following. So the length is bounded above by 2000, which determines the problem size. And the numbers can be 0, can be negative, and can be positive. So this basically means k times m is bounded above by the length of the array. So this makes sense. So here m is at most 3. We should pay attention to the lower bound. M is greater than or equal to 1, which will be used in our coding. So with that said, I guess we are ready to do the analysis. So in this video, my plan will be the following. So first, I'm going to do some abstract analysis. So this actually makes the coding and also video more rigorous. And also, it should be accustomed to abstract thinking. Then based on the abstract analysis, we are going to do the coding. So the coding is nothing but translating the analysis into coding format. So after we do the coding, we are going to do some print and walk through the two examples here. So with that said, I think we are ready to do some analysis. So you can use example 1 as a prototype problem. So here I'm going to introduce a 2D dimensional table. So here ik means the maximum sum possible. So with this subarray, so in other words, from the index I and onwards, right? So forming key non-overlapping subarrays. So then this is our interpretation. So this will be very important. Actually, for dynamic programming with tabulation, so how to interpret or what interpretations do you choose determines the DP update rule. So once we know this, right? So we want to, if we are given DP I bar and K bar, where I bar is larger than I, because so we use from I onwards if we know some, and then we extend to the current I, and the K bar is less than K. So how to determine DP IK? In other words, what's the DP update rule, right? So this actually can be analyzed as like this. So DP IK by its interpretation will be the larger of the following two. First, if I do not use list starting at I, then I just need to consider this part, right? DPI plus 1 and up to k. Then basically from the index I plus 1 and onwards, so what's the maximum score, right? If we form k substrings. So this is the one. Another one is we use the current number. So if we use the current number, so this current number should be an element in an array with length at least m, right? So assume, because the start is fixed as I, and the ends can be different j's, that's why we use endings. So the length, that is j minus I plus 1, should be greater than or equal to m by the problem assumption. So we pick the maximum among all those. So maximum, so assume that the subarray starting from I, ending at j, right? Then we need to have the sum of this part, this array. And then from the g plus 1 onwards, because here we are ending at g, and we just need to form k minus 1 substrings, right? So in other words, this maximum will be taking over j such that j minus I plus 1 is greater than or equal to m, the length constraint. Let's call this one the start. So this part is rather straightforward, right? So we focus on star. So here actually we assume that Si will be the prefix sum ending at index I. In other words, the prefix sum of starting from 0 up to index I, right? So then if we use this same notation, the prefix sum, we can simplify or transform star a little bit, because the sum of this element from I and ending at J will be Sj, right? And minus Si minus 1. Notice here the index I minus 1. Then plus this part, right? But notice that we are taking maximum over J, so this part does not come into play. We can break it outside the bracket to get this one. So we call it star again. So now we just need to compute this quantity, right? So once we know this quantity iteratively, because originally we have k minus 1 equals 0, then k minus 1 equals 1, and onwards. So we can define this quantity, this one. So we can define this I k minus 1 as j greater than or equal to I, right? So in other words, for those quantities, I take the maximum over j when j is no less than I. So this quantity will be nothing but corresponding to this one, I plus m minus 1, right? This is star at k minus 1, then minus this s minus 1. This is just a translation. So now let me explain again. So if we use this definition, right? So this part is nothing but qi plus m minus 1, right? Then minus this si minus 1. So now let's look at this. What's the recursive relation of this one? So let's actually this quantity. So this quantity, let's see, q I k minus 1. That is, by definition, it's a max. So let's just copy this part. Max for j greater than or equal to I. So then if I write like this, I plus 1, right? Then I should write this, also add this corresponding to I, right? So the max of, let's use this or to represent the max. That will be j at I equals I, right? So that is qi k minus 1 is max. So this part, by definition, is nothing but qi plus 1. So this part will be si dp I plus 1 k minus 1. That's the recursive relation. So once we have this called double starless, then we can do this, do the whole thing in O of n, right? Originally, if we just do like this, so we consider all the possible possibilities, j minus I plus 1, and then this will be O of n squared. Just using big O notation, roughly estimate. So once we have this, so we know if we know the k minus 1 equals 0 case, then we know all those things. Then basically we know the item here. Then we can get the solution for the problem. Right. So what we are going to return, actually, our return will be the following. Return, because dp ik, right? I'm going to change this little k to be capital Q, k. So we are going to return the max, right? So you can start from over I, right? I is say greater than or equal to 0, less than or equal to n. If you start in onwards, you get 0. So you can write n minus 1. It's also okay, same thing. So that will be the whole idea. Hopefully you get the main point, right? So now what do we want to do? So with the above interpretation, so we can write the code. For write the coding, let me first get n, length of nums. So this is just for convenience. Then also we need to compute the prefix sum. So I can use 0 times this n. And let's first fix the prefix sum. That's rather straightforward. So for I in range n, right, if I equals 0, so Si will be nums I. Otherwise, I will be larger than 0, so Si will be the previous sum, that is Si minus 1 plus the current number. So then this is the prefix sum or partial sums. So now let's initialize the DP table. So the DP table will be, say, I'm going to use float negative infinity times, because we have k plus 1 possibilities, right? Forming 0, forming 1, or forming k. And then for a dummy index in range, so I'm going to use n plus 1. So in other words, the largest index will be n. So from n onwards, you have empty one, you're for sure to get 0, or you set it, the sum will be 0, right? So now let me first do some initialization. So for I in range m plus 1, so dp I 0. In other words, from each index and onwards, if we just do not consider any subarray, the sum for sure is 0. So this is the one. So now I'm going to define this part, the qi key, right? qki minus 1. I'm going to call it sub best. That's going to be float a negative infinity. So times, so n plus 1, right? Because I is in the range this one. So for this, we can also, you can see I'm do initialization for corresponding to k minus 1 equals 0, right? So in this case, let's see, for I in range, so n minus 1, negative 1, so we start from small to larger. So the sub best I will be the max of sub best I plus 1. So I'm using this this formula. Then Si plus this one. So here, because k minus 1 is 0, we do not consider any subarray. So this term is going to be 0. Then Si will be, let's see, just Si, right? You can interpret this corresponds to k minus 1 equals 0, right? In other words, C Q I k minus 1, the definition. So what we are interested in actually is Q I plus M minus 1, right? The Q, the I plus M minus 1 is from here, right? So now we have this preparation. We can look at the general DP update. So we are going to do for k in range. So because we have considered the k equals 0 case, so we'll consider k equals 1 up to k, right? And then for I, because our interpretation from I onwards, we are going to do reverse iteration from n minus 1 to negative 1 to 1. So this ends before negative 1, that it will be 0, right? So then first I'm going to check if I plus m minus 1 is less than n. The reason I'm checking this because I'm going to write the next line. So dp ik would be max. So dp I plus 1 and k. So this is the first item in the analysis. That is this part. So also we need to include the star, this part. But this part can be given by here, right? So what we want to do is sub best. So at I plus m minus 1. That's why we're checking if it's less than n, right? So then it's going to minus this si minus 1. So, but I can be 0, so we are going to do this si minus 1 if I is greater than 0. Else it's just minus 0, right? So this is the max sub. Let's see. We don't need this this part, right? So so here we are using, because here we are consider k, so we need to DPI key. So we're going to use k-1 case. That's the initialization here, because k equals 1, so we are going to use 0 case. So this is the one. And then we are going to update this subbest for next round. So we are going to do subbest. This next round still float negative infinity times n. And then we are going to do one update for I in range n-1, -1, -1, right? So subbest I would be max of subbest I plus 1. And then the general formula is this, right? Si, right? So that will be Si plus dp I plus 1. So here is not k-1 but a k, because we are preparing for this next round, because currently we are considering k-1, right? So next round will be k. So once we have this, we just need to return the max of dp I k for I in different start point in range. See, you write n, that should be enough, but you write n plus 1 is also good, because the last one is 0, right? So let's check that. Yeah, it passes all the cases. So now let's see, list auto range. So subbest 80. This will be here 1. So I should write I plus 1. Let's submit. Still, let's see, subbest I and max subbest I plus 1, then Si I plus 1 k. What's the problem? Let's see. For I in range, this is the right. Let's see. Where's the best float infinity? Oh, here. I guess I should write n plus 1. Now let's submit that. Yeah, it passes all the cases. So yeah, again, as I mentioned, you can write n here even. Let's submit that. So by far, actually, we finished the second part, that is the coding part. So next, I want to do some print so that I can walk you through the two examples quickly. So here, we just need to pay attention to the DP table. So let me print for row in DP, print row. So now let's run it. So now you see this has length 6. So we're going to k equals m length. K is 2, right? So the length will be at least 2. So here we're going to have 7 by 3. 7 is the length plus 1. 3 will be k plus 1. So now let's examine from this line to the first line. So if we start from this 1, 0 up to say 5. So if we start from 6, we don't have any element. So the sum will be 0. So forming a 0 element subarray. If forming a 1 subarray, it's impossible. 2 also impossible. So now if we start from this element, that is index 5. So forming the maximum sum, forming 0, that would be 0. Forming 1, also impossible, because the length should be at least 2, right? Because here we have only 1 element. So that's the this line. So now if we start from the 3, 4, this corresponds to this line. So forming the 0 subarray, so you're going to get sum 0. Forming 1, that will be the sum of this one, that will be 7. Forming 2, it's impossible. You have to split that one, but and then you will break the second constraint. The length will be 2. That's why we at least 2. That's why you have negative infinity. So now let's start from this 3. Then we have 3 numbers, 3, 3, 4. And then forming 0 subarray, you have a sum 0. Forming 1, that it has to be the sum, that is 10. Forming 2 is impossible because we need each one have length at least 2. We need to have at least 4 elements, but here we have only 3. So this line. So now let's start from -1, right? So this corresponding to this line. So forming 0 element, 0 subarray, you have sum 0, and forming 1, it's going to be the sum, right? With the largest will be this sum, and forming 2, it's possible, but it can only be like this or this, right? So we have 2 plus 7, that is 9. This is the last number. So if you start from index 1 corresponding to this row, then forming 1, 0 subarray, for sure you get 0. Forming 1 is just the largest one. It will be the sum, right? So 1 plus 10, that will be 11. So forming 2, it's also going to be 11. You can, for example, do this one and this one, or you do this 3 and this 2. Then starting from 0, so the whole array. So you want to forming 0 subarray. So that will be 0. Forming 1. So if you want to forming 1, this actually corresponds to the sum. So this is going to be 12, right? Because this is 1 and -1 cancels. You have 2 and this 10, 12. But forming 2, so what you can do is you can form this one, that's 3, and then use this 3 number, that's 13. So this is the first example. So similarly, you can analyze the second example. So for the second example, so the length and just not empty, that will be fine, but we need to form 4 subarrays. So if you start from nothing, you get 0 and infinity, infinity, that's for sure. Then if you start from -2, forming 0 subarray, you have some 0. Forming 1, so that's only itself, that's -2. Then forming 2, 3, and 4, they're impossible. You get -3, negative infinities. And then if you start from -1, so forming 0, the sum will be 0. Forming 1, so that will, the largest will be -1. And then forming 2, that will be -1 and -2. The sum will be -3. Forming 3 and 4 is impossible, right? That's the 2 infinities here. And then you start from 3. So forming 0, you're going to get 0. Forming 1, so you just use the 3, the largest. Forming 2, you can use 3 and -1, that is 2. Forming 3, you have to choose this 3, each single element subarray. The sum will be 0. Forming 4, it's impossible because we have only 3 elements. So then starting from index 0, forming 0, you get 0. Forming 1, you just use -3, right? Forming 2, so you can use positive 3 and -1. You have a 2. Forming 3, you can use this 3 as each element as a single list, get 0. And forming 4, you have to use each element as a single array. So the sum will be 3, -1, -2 cancels, you get -10. That's the number. And that's also the detailed walkthrough for this one. Hopefully, this walkthrough help you better understand the logic of this problem. I guess here, what I want to emphasize is that, so when you do DP, especially in the current tabulation format, it's very important to make it explicit what's the interpretation you are going to use. And then, based on the interpretation, you are going to get DP update rules. So here in this problem, I guess the trick is how to do some memory and to avoid computing those things here using a square term complexity component, right? So that will be the full point. And here, this abstract analysis actually is very straightforward. It helps understand the procedure and the coding. So if I just directly write in the code, it will be hard to digest. But if we do this analysis, then you make a correspondence with the formulas and the coding. So then things should be more clear. So with that said, I guess that's basically about it for the current video. And before we end this video, let me give you some extension. So similarly, you can do dp update rule, like I define dpij, like the maximum possible sum by selecting, say, j subarrays using first I elements. So then the question is, can you do similar analysis, actually parallel as above, and then write a DP solution with tabulation? So that would be a very good practice. This extension will help you really digest the idea here. With that said, thank you for watching.